From power generation to medical treatment, nuclear physics has many applications in today's world. Even a small step in the field of nuclear physics can have a major impact on finding a solution to some of the world's greatest demands. An atom is made up of a nucleus and electrons. Within the nucleus, there are protons and neutrons. Nuclei play an important role in the making of matter in the universe. They serve as fuel for stars and can also be studied in the laboratory. The field of nuclear physics studies the building blocks and interactions of atomic nuclei. Recently, a group of scientists at the University of British Columbia has discovered a new way of understanding an exotic and unstable type of nuclei called neutron halo nuclei. Dr. Sonia Baca and her team of researchers made the first ever direct mass measurement of one form of helium, called helium-6. This discovery not only determined the exact mass of the lightest known halo nuclei, but also serves as a benchmark measurement for the field of nuclear physics. Canada's National Laboratory for Particle and Nuclear Physics, TRIUMF, houses the world's largest cyclotron and was the site for this first-time measurement. Dr. Baca, the lead theorist for the study, explains the novelty of this mass measurement and its advantages over the previously used theoretical calculations.
It was not available before, so before we had only access to this older data which suffered from large error bars, and we wanted to have a better constraint on this observable. So having a direct measurement of helium-6 and helium-8 mass means that we can have a value of that number with a very small error bar. This is important for two reasons. First, we know the mass of the nucleus better, but this serves us also to know the size of nuclei better.
The old mass measurement was highly inaccurate, as it was based on theory alone. However, having the direct mass measurement provides scientists with more accurate data. This sort of information is key to figuring out how nuclei interact. Using TRIUMF's world-class facilities, including the Titan penning trap mass spectrometer, Baca and her team discovered new information about nuclei interactions.
And by comparing the best experiment available from Titan and a series of state-of-the-art calculations available in the literature, what we found out is that we have to assume that nucleons not only interact in pairs, but they can also interact in triples.
With the more precise masses, we have a better understanding of how nuclei interact. From that, we advance our knowledge of the universe and ultimately what we are made of. However, this direct mass measurement also posed many experimental complications. Helium-6 is an unstable nucleus, and it only forms for a fraction of a second. This means that the experiment had to be conducted within a very short time window. In addition, there is great risk when dealing with unstable nuclei, as Dr. Anya Kwiatkowski, the lead technologist, explains.
So, for example, the most, I think, obvious risk is that we're dealing with an unstable nucleus, so there is going to be radiation present. So how do we minimize radiation and ensure that no one is exposed to dangerous levels of radiation?
Nonetheless, this first-time measurement is an essential piece to add to the puzzle and has the potential to save lives one day.
Ultimately, basic science wants to improve health and the quality of life, and it does, and there are examples to prove it.
Tim Meyer, head of strategic planning and communications at TRIUMF, provides one such example and sums up the importance of advancing knowledge in the field of nuclear physics.
So we look in the field of medical isotopes. We use isotopes right now for a lot of imaging purposes, but it'd be great to actually use some of those isotopes maybe with a different property, a different decay mode, a different type of nuclear or chemical property that can actually deliver therapy to someplace in your body. And one of the constraints we have right now is we can't actually predict which isotopes are going to be those magic ingredients for treating cancer or dealing with disease in your body. So as we uncover this fundamental understanding of nuclei, we can actually make steps in actually predicting what nuclei will have what properties that we can use for the demands we have right now.
One day, such a therapy or such a treatment may exist. However, for the time being, researchers hope to continue to create a better understanding of nuclei, like knowing the mass more precisely. And perhaps, in the near future, nuclear physics can be used to save lives in new ways.